Okay, so thank you everyone for coming to the last talk of the semester for our seminar. And today it's a very big pleasure to have Danka Lucic. I tried to pronounce it the best I could. And from the University of Jyväskylä, she's going to speak about from perimeter minimization to BV extension sets. Thank you very much, Danka, for accepting our invitation. Please go ahead.
Well, thank you, Chucho. Thank the organizers for inviting me to give this talk. It's really a pleasure. And so today I'm going to speak about BV extension sets in a general setting of metric measure spaces. But to introduce you to the topic, let me start by a brief overview of what happens in some more familiar setting, that is that of Euclidean space. So what do we mean by an extension domain or an extension set for Sobolev or BV functions? So let us look at the Rn equipped with the Lebesgue measure and take omega to be a domain, open and connected set, and take any exponent p from 1 to infinity. And now this is a question that has been asked a long time ago, as we will see in a few slides, by many people and for many reasons. So can we find some constant c and the map from the Sobolev space on the domain omega to the Sobolev space over the whole Rn, which satisfies the following properties. So this extension of every Sobolev function on omega restricted to omega itself is giving us our initial function u, and the norm of our extended function of Sobolev norm on the whole space is controlled by this constant times the Sobolev norm over our domain. So the same question can be phrased by using just the space of functions of bounding variations, so BV functions over omega, and BV functions on Rn as the target of our operator. So I just recall here that we are talking about functions that are P integrable and whose distributional derivative exists in this P integrable in the case of Sobolev functions, and in the case of BV functions, distributional derivative exists as a measure. So when we have such a map, extension map, we will say that the domain is a Sobolev or BV extension domain, and the map itself will be called extension operator. So now, why do we care about such domains or such maps? So some classical problem in analysis are concerned with the minimization of the Dirichlet energy functional, which associates to every, say, smooth function the Dirichlet energy, which is the integral of its gradient to the power p. And if we relax this, take a lower semi-continuous envelope of this functional, and consider also our functions u with the prescribed values on the boundary, so we want to find some minimizers of this kind of energy, prescribing the values on the boundary of omega. So now, when we relax such a functional, so we are passing from the set of functions which are smooth to the set of Sobolev functions or the BV functions in the case in which p is equal to 1, which are not so regular, and it is difficult to say what is the value of such functions at the boundary. So in order to make sense of such a problem, one needs to know how to extend the function, which is a priori defined only in omega, to its boundary, and also to determine for which boundary data this problem is solvable. So somehow this is one of the many motivations to study extension sets. Now in a moment we will see also how is this related to the extension itself. So The first understanding about these extension domains dates back to the 60s and 70s by the works of Calderon's time and the Italian school by Gallardo and Anzelotti Giaquinta, where they have proved that actually in the case of Euclidean space, every bounded Lipschitz domain is Sobolev for all exponents p and also be the extension domain. And once we have a bounded Lipschitz domain, and we know that it's extension domain, then one can show that actually we can define trace of a given BV function on the boundary of omega. What does this mean? So it means that for n-1 Hausdorff measure, almost every point x at the boundary, there exists a value such that this average integral over a ball by sending r to 0 exists, the limit of this average integral exists and is 0. So we can prescribe a value to almost every point at the boundary. And being our domain an extension domain, we can also get good bounds for this trace operator. So we can bound the norm of the trace operator by a constant and by the norm of our given function on the domain omega. And this constant is given in terms of the extension constant coming from the extension property of the domain. So this is somehow a motivation and the relation why should we care about such domains. So now we have seen that actually we have extension domains, so there are many of them. All bounded Lipschitz domains are extension domains, but actually there are much more. There is by a result by Jones is telling us that all uniform domains in the Euclidean space are Sobolev extension domains, and the domain is, so what are uniform domains? So all bounded Lipschitz domains in particular are uniform domains, but this class includes much more. And domain is uniform if there is a constant, so that every 2 points in our domain we can connect by a curve gamma, whose length is controlled above by a constant times the distance between the points. And if we pick any point on our curve and take subcurves from x to that point z, and the other subcurve from z to the point y, then the minimum of the length of these two subcurves is controlled by the same constant times the distance of the point on the curve to the complement of omega. Okay, so if you want to think about a domain which is not uniform, you can imagine an infinite cylinder, for instance. This can be easily seen that it is not a uniform domain. But we will see in a couple of slides also some bounded domains which are not uniform. Okay. And after we have discovered that there are many extension domains, so people started study their characterizations and some geometric properties, and the literature is really vast. So I am here selecting only some of the results that are maybe nice to mention. So for instance, by work of Haiwas, Koskela, and Tuominen, we know that extension domains have measure density property, which in particular implies that such domains have boundary, have boundary whose measure is 0, and that in the case of in which p is greater than 1, the operator we construct is linear. This, for the case p equal 1, in general is not true or is not known. Then by the work of Schwarzman and later generalized by Koskela, Rajala, and Zeng, we have a characterization for planar simply connected domains via some curve conditions. And these, together with some previously known results, say that in the case P equal to uniform domains actually are characterization for extension domain. So you are, if you are in the Subole space W12, then being uniform is equivalent to being an extension domain. And what we have also studied in collaboration with Tapio, Rajala and Danka Lucic are some some bounds or the house of dimension on the boundary, for instance. And as I already said, people study many other questions about the extension domains. And for what regards BV setting, Burago and Mazia have given some characterizations of these domains in terms of extendability of sets of finite perimeter that we will see, because it will be one of the properties that will be important also for us. So basically, this means that you can look only to the extension of characteristic functions in order to conclude something for all the functions. Then Koskela, Miranda, and Shannon Gallingham proved that the domain in the plane is a BV extension domain if and only if its complement is quasi-convex. So quasi-convex, it means that there is a constant, so that every 2 points in the complement you can connect by a curve going from x to y, so that its length is again controlled by the constant times the distance between 2 points. And finally, Garcia Bravo and Rajala studied relations between W11 extension domains and BV extension domains. So now, as I said, there are many already in the Euclidean setting, there are many extension domains, but there are also some domains which are not extension domains. So for instance, if we look at the slit disk, so we take a ball and just we are taking out this small slit, then we can show that this is not W1P extension domain, but it is BV extension domain. So to see that this is not W1P, just you can take a function which equals 1 up here and equals 0 below, and you can make it such that it is in W1P of the omega itself. But if you want to extend such a function, it will necessarily have a jump when you are looking to the curves passing from the one side to the other. And this is saying that it cannot be extended to a function which is in W1P of the whole space. But this is in BV, because in BV we are allowed to have jumps. So, and also by the characterization of quasi-convexity of the complement, one can easily see that this is a BV extension domain. To see something that is not BV extension domain, one can do something similar with a lot of slits. So in this case, if you are starting to accumulate these slits, then function will, for the same reason, function will have to jump, but many times, and it will be infinite amount of times. So with a jump, for instance, from 1 to 0, from 1 to 0, and this is going to be infinite. Another example of a domain which is not BV extension domain that one can see by just looking in this geometric characterization by the quasi-convexity of its complement is this cusp domain. Because if we look at the complement of this omega and take 2 points, one on this side and the other on this one, and try to connect it by a curve, then we can, if we are going really near with the points to this cusp, so their distance will be really small, while the curve will have to, so imagine that this cusp is really, really, really thin here. So the curve will have to have a certain length, but the distance between the points can be arbitrarily small. So this is something that destroys this property of being quasi-convex. So if we really want to work with domains which are not extension domains, but we still want to address some minimization problem of some functional over our domain, so we can ask ourselves, can we still do something? Can we approximate maybe our domain in measure from inside or outside by an extension domain? And actually, in the Euclidean setting, every bounded domain can be approximated in measure by Lipschitz domains. So we know that we can do something like this. So now all of these questions were in the Euclidean setting, but actually one is allowed to change the setting and is also motivated to change the setting. Why? Because we can be interested also in the minimization of the Dirichlet energy functional that I showed you before, where the energy itself is not with respect to the Lebesgue measure on Rn, but with respect to some arbitrary Radon measure on Rn. Why is this so? Because, so let's do some concrete example. So for instance, our domain can be think of as a material whose conductivity, for instance, is given by the measure mu. So, and then over this domain, you would like to find the best temperature profile, which is represented by your function u in the Sobolev space, and the energy and this temperature profile you are finding by minimizing the Dirichlet energy, and you are integrating over the whole domain with respect to the measure mu, because this is something that is representing your conductivity property. So some physical example like this is telling you that, okay, but then when you relax your functional, being in this setting, starting from the smooth functions, you end up in the Sobolev space, but now over the space which is Rn, equipped with an arbitrary Radon measure over it. And this is just a specific case of a metric measure space that we are going to see in a moment. So also it is not that we want to stay also only on Rn, but maybe our domain can be something, some domain in a Riemannian manifold, or it can be a sub-Riemannian manifold, also infinite dimensional Gaussian space, or limit, Gromov-Hausdorff limit of Riemannian manifolds with some curvature bounds that are leading us to the setting of non-small spaces with curvature bounds. And in order so to provide a unified theory about all of them, it becomes natural to look at the setting of metric measure spaces. And what do I mean by metric measure space? I mean a complete and separable metric space endowed with the boundedly finite Borel measure mu. So a Borel measure mu, which is finite on bounded sets. Okay. So let me tell you, first of all, before addressing the problem of extension of BV functions in this setting, so let me tell you how they are defined. So in the metric measure space setting, there are several notions of Sobolev and BV functions, and the one that will be useful today for us is the one via relaxation, as the definition that we already saw. So looking at the Dirichlet energy functional and taking the lower semi-continuous envelope of this. And in the Sobolev case, such a definition is due to Shiger, while in the BV case, it's due to Miranda. There are other approaches that you might know. Some of them are looking at the behavior along curves, or like this distributional approach via integration by parts formula. And in the BEV case and in the case of P, which is strictly greater than 1, all the definitions are shown to be equivalent by the work of Di Marino. while the equivalence for W11 is also true, and it will be the result in the forthcoming paper by myself, Ambrosio, Tony Conen, and Enrico Pasqualetto. So to define BV functions instead of smooth functions in this metric setting, we are going to use Lipschitz functions. And what will play the role of the modulus of the gradient that we are using to define our energy, in this case will be the asymptotic Lipschitz constant, which is for every locally Lipschitz function defined as the infimum over all radii R of the Lipschitz function of a function u restricted to the global Lipschitz function of the function u restricted to the ball of radius r, and then you shrink the ball around the point. Okay. So once we have this notion of asymptotic Lipschitz constant, we can just for every Lipschitz function take this Dirichlet energy and then take infimum over all the limits where we are taking sequences of Lipschitz function converging to our function Q in LP. And whenever for any U which has finite energy, we say that it belongs to the space of Subole functions when P is greater than 1, while when P is equal to 1, we end up in the case of BV functions. Okay, and we can also, in the BV case, we can also localize this definition, and in this way get the total variation measure associated with the BV function U, and this measure for every open set is defined exactly as above. Just the convergence is taken in our open set A, and the functions are locally Lipschitz function over the set A. And then for every Borel set, we can do the standard character of the reconstruction to get really a measure. Okay. So now what we will be interested in is the total variation of a particular function, which is a characteristic function of a set. So now, given any Borel subset of our space, we say that the Borel set E has finite perimeter on a fixed set B. So there are two things. We can look at the perimeter of the set E in B, which means that this is the total variation of the set, or total variation of the characteristic function of the set B when computed in the metric measure space as it is. So the one we fixed from the beginning. We can also look at something else, so we can restrict our measure mu to the set B and look at the same quantity but computed in this space. And these are two different notions, and you can see that they are different by directly looking, for instance, taking the set B to be a closed set and taking set E to be B itself. So then you with this notion, you are taking into account the boundary of the set B, but with this one, not, because you are looking only inside B. Okay, and this will be an object which will play an important role in what we are going to do. Okay. So when B is the whole space, we will just write perimeter of E, and it is, call it perimeter of the set E. So just to remind from the classical setting what is this notion. So the perimeter of E in the classical setting is the total variation of the characteristic function, and actually this total variation is the total variation of the vector valued measure that exists. In the general metric measure space setting, as we will see in a moment, this does not necessarily exist. Also, something that we know in the Euclidean setting is that the perimeter measure of a set E is nothing but the n-1 dimensional Hausdorff measure restricted to the boundary, to the essential boundary of the set E, where this essential boundary is just a set of points on the boundary of E, on which both the density for the set E and its complement is positive. And as I said, in this general setting of metric measured spaces, we might not have the underlying vector valued measure underlying the total variation. Because in the metric measure space setting, the notion of Subole function and BV function came naturally with the notion of weak upper gradient, which represents in a sense modulus of the differential, but at the first appearance of of the definition of Subole function, there was not differential itself. Actually, due to the work of Gili, we know that we can speak about actually the differential of Subole function, whose modulus is precisely the weak upper is equal to the weak upper gradient. And this is true for Subole functions, but in the case of BV functions, we do not have this vector valued calculus yet in the full generality. Also, something that we have in the case of PI spaces is that the perimeter is not precisely so it is a codimension 1 Hausdorff measure restricted to the essential boundary of the set, multiplied by the density function, which may depend on the set E itself. So this is somehow in the PI setting, we have this analog of Hn-1 measured or restricted to the boundary, to the essential boundary, but with this density function. Okay, so this was just a side note just to tell you that the theory is developed and there are some things that are good as well as the Euclidean setting, but from this we can see that the setting is much more general and it lacks some the properties. And just briefly to recall, so the PI spaces are, we mean by PI space, I mean the metric measure spaces where measure has a doubling property, so this one, and satisfies a local 1-1 Poincare inequality. So I will mention, we are going to work in general metric measure spaces without any assumptions, but given that in PI spaces, sometimes we have something better, and I will mention them from time to time, so just to remind you what they are. And so a result which I find nice by itself, and which was useful for us to get our main result is the following. Given that we are talking here about the extensions, this is something about extension of Lipschitz functions. So result by Di Marino, Gili, and Fratelli, which says that given a metric space and a subset C and a Lipschitz function G, then for every epsilon we can find a Lipschitz function whose Lipschitz constant will be epsilon close to that of G, whose restriction to C coincides with G itself, and for every point of C we have that the asymptotic Lipschitz constant coincide. So we are preserving asymptotic Lipschitz constant, but we have to change a little bit the global Lipschitz constant. And actually, this is sharp, so we cannot preserve both of them. This can be seen by an easy example. So if you take your space to be a unit interval and your set to be just a set of 2 points, 0 and 1, and the function G to be defined as G of t equal t, so 0 and 0 and 1 and 1, then global Lipschitz functions of G is 1, asymptotic Lipschitz function of G is 0. But if you would like to extend this function, preserving the global Lipschitz constant, the only possible extension is f of t equal to t, which has asymptotic Lipschitz constant equal to 1. So we cannot preserve also this. And this result has a nice consequence, because once we have a closed subset of a metric measure space, closed subset if we restrict the measure to the set itself and the distance as well, then this becomes a metric measure space itself. And what follows from this result is that the space of VV functions over X, D, and the mu restricted to C is the same as the space of VV functions over the space C itself as a metric measure space. And now, as I said, BV extension sets in this generality has been studied by Caputo, Koivu, Rajala, and this definition of a BV extension set has been given in this recent paper. So they say that the Borel set is a BV extension set if we have this extension operator now starting from the BV space over the metric measure space where the measure is restricted to B and going to the set of BV functions over the whole space with the usual properties that we have seen already at the beginning. And something else that we will see that will be equivalent to having this, to being extension set is extension property for sets of finite perimeter. And we say that the Borel set has an extension property for sets of finite perimeter. Basically, if we are able to extend to do the extension for the characteristic functions. So if for every subset of P with finite perimeter, we can find the Borel subset of the whole space so that this inequality holds, which is nothing but these one applied to the characteristic functions, and the measure of this difference is 0. Okay. So what's already known is in PI spaces, again, Koskela, Tuominen have studied Subole extension domains. And again, in PI spaces, we have many good things as in Rn. So there are measure density conditions, linearity of the extension operator. Then it has been also shown by works on Bjornsen, Gallingham, Lahti, and co-authors that uniform domains are Sobolev and VV extension domains also in this setting. And they have done a lot of work also on the trace theorems for VV functions. Baldi and Montefalcone generalized the result by Burago and Mazia about the characterizations of extension domains in terms of extension property for the sets of finite perimeter. Then by Rajala, we know that in PI spaces, we can approximate every bounded domain by uniform domains, which are by this previous result extension domains. So we have this approximation property. Then there was interest also in the extension domain, even in the Gaussian spaces. And as I just mentioned, in general metric measure spaces, the first work that appear is about the relation between W11 BV extension and the extension property for sets of finite perimeter by Caputo, Koivu, and Rajala. So what do they prove? And will be something that we are going to use. Next is that the Borel set is a BV extension set if and only if it has the extension property for every Borel set of finite perimeter or equivalently every open set of finite perimeter. And we are going to combine this above result in what we are going to study with the following property. So this is a property which regards only the perimeter of a set. It's an inequality. And it says that once you have a closed set and a subset of finite perimeter on B, then the following inequality holds. So what does this mean? So first of all, why do I have to have a closed set here? Because for an open set, we have an example which now I show you here, that this can fail. So if you take your set B to be an open interval from here to here, and take out also this point from this open interval, so you are union of these two open intervals, and take the set A to be this precisely this interval here, then the perimeter of the set A in the whole space is 2. Perimeter of the set B minus A is again 2, so you have 4 on this side. Perimeter of the set P in the whole space is 2 as well, but the perimeter of the set A in B is 0. So you have 4 less or equal than 2, which is false. So this lemma holds for closed sets. And this in this example here, you can easily see that 2 is really needed here. If you chop out this part, this interval, for instance, from the big interval B, then you will see that it's really, you cannot put here less than 2. So it has to be at least 2, this constant. So we are going to combine this characterization of the extension sets with such a property of perimeter to get the result that we like. So what we are going to study, approximation of a given domain in a general metric measure space by the extension sets. So this is our question. So given a bounded domain and given an epsilon, we are asking ourselves if we can find an open or closed with extension set or a domain which approximates omega from inside or on outside. So there are many questions in measure, so that the measure of the difference is less than epsilon. So in order to address this question, in this generality, we are not using a constructive way, but we are rather using a minimization of a functional, which is going to be defined as follows. So for every lambda, we define a functional of the set of Borel functions as the perimeter of a set plus lambda times the measure of the symmetric difference between our domain and the Borel set. So now, first of all, let's forget for the moment about the approximation in measure, but how one can show that a minimizer of this functional can give you an extension set for PV functions. So suppose that for some lambda, this functional has a minimizer. Now pick any subset of your minimizer G lambda, whose perimeter in G lambda is finite. And by the minimality, you just use the minimality of G lambda, and this set is another candidate, and this is this inequality followed by the minimality of G lambda. So this is something that you have. Then let us suppose that this G lambda is a closed set, or more in general, it's enough to say that it has a closed representative. Then by lemma that I just show you, and so this is why I am assuming set is closed, we also have this inequality applied to G lambda and as its subset, the set A. And if you combine this inequality with the previous one, you easily get this inequality here. But this, taking as the set A tilde in the definition of your extension property for the set of finite perimeters, so basically extending to 0 characteristic function out of A, so you are getting precisely that you have the property, the extension property for the sets of finite perimeter. So then you can conclude that your G lambda is a BV extension set by a result of Caputo, Koivu, and Rajala via this 0 extension. Okay. So one thing is that G lambda has to be closed, and the other thing is now one would like to approximate either from inside or from outside. So in order to get something that can be useful once you want to treat maybe some minimization problems or any other problem you would like to use for the extension domains, And this procedure actually from you can see from here that this is stable if you would like to do it some approximation from inside. Why? Because if I would like to do this outside, I wouldn't have something to compare with this if I want to stay in the same class of sets. Because if I'm approximating from inside and taking out something of my set, it is still inside. But if I'm from outside, this property is not anymore satisfied. So those are two reasons why this kind of procedure is telling us that maybe we can get something by trying to approximate omega from inside and by a closed PV extension set. Okay, and now for our functional M lambda, one can show that it has minimizers among all Borel sets, but in general, and we will comment later about this for some specific cases, we do not know if a minimizer has a closed representative. So what do we do? Okay, so this is what we show. So let's our xt mu be a metric measure space and let omega be a bounded domain. So given epsilon, we can find a closed PV extension set G, whose so that the measure of the difference is less or equal to epsilon. And given that we are approximating from inside, so it is enough to look to the closed subset of omega. And our functional on the closed subset of omega look like this. So something that you can show is that infimum over all closed sets for every lambda is finite. And we can show that we can find lambda, depending on epsilon, big enough so that once you take a minimizing sequence, you can, if you pick I which is the index of your sequence. So if you pick I big enough, then the measure of omega minus this C lambda I will be smaller than epsilon. And why is this? Because this lambda is competing with this measure of the omega and difference of omega and C. So you can find lambda big enough so that this is getting small enough in order to minimize the whole function. Okay. And now you have found this set which is near in measure. And this is somehow giving us, and it is closed, but we almost have our candidate for the PV extension set. So now we take all closed set subset of omega where the functional is finite, and we can on this set introduce a partial order. So we say that A precedes P if and only if the measure of the difference is 0 and if the functional if the functional computed at A is less or equal to the functional computed at B. And what we can show now when we take this, our good element of the minimizing sequence, and we take all the closed subset in which functional is finite, which are less with respect to this order than our C lambda I, then this set, by using Zorn lemma, has minimal element. And we call this element G. What now is how do we conclude? The minimality is this, in this sense, is enough to use again the same procedure as I was showing here by using the minimality, really the minimality of G lambda, but still this kind of minimality is enough to use the same procedure and show that this is a PV extension domain. And it will still have this property because we took the set in this class. Okay, so this is how we overcome this problem. So now one could ask if such a G we obtain, or also more in general, if a minimizer, if it would exist closed, has an open representative, and even if it does, is that open representative still an extension set for BV functions? And actually the answer to both questions is no. And this we are going to see in two examples. Okay. So in the first example, I'm going to show you a BV extension set which does not admit an open representative. So our setting is the Euclidean plane, and now with the following measure mu. So our measure is a Lebesgue measure weighted with this weight, which is 1 everywhere apart near to this line and near to this line when it's comparable to the distance to the line. So it's going to 0 when you are closer and closer to this line. And then you also sum the Dirac deltas which are centered at these points, which are center of the base of these triangles, weighted in a good way, so you can get something finite. So, and the domain you are looking at is this square, say unit square, and above it you are attaching the properly scaled sequence of triangles so that they are accumulating to 0. And what is also the part of our domain are these bases for the triangle. So it is a square together with this base and the triangle. So, and now, due to the choice of this weight and this behavior that it is 0 near to this line, so what can show is that, so now we have a minimizer among all Borel sets, we always do, and what we can see is that this common part is convenient to be in the minimizer. So this one can show. And also something that is due to this choice of weight is that you can split your functional and look at it separately in the square and what is happening in the triangles. And once you have that a minimizer of your functional, then if you intersect it with the closed triangle, then it minimizes the functional inside the triangle itself. So it minimizes, say, this part. And so now, in order to show that a minimizer does not have an open representative, the idea is to so you have to show that it has a boundary whose measure is positive. So how do you do this? So as I already said, minimizer will contain these common parts. But what we can show is that for lambda big enough, and for n big enough, we can find a triangle where in the triangle, so the intersection between our minimizer and inside the triangle, there is nothing in measure. So the L2 measure of this intersection is 0. And this you can show by exploiting the minimality. This and the fact that perimeter of a point inside the triangle is 0. And this is something which is due to the choice of the measure itself. And this is giving you that in measure, your minimizer intersects this triangle Tn for n big enough. In measure, it intersects only this common part. And what does this mean? This means that the point xn has to belong to the boundary of your minimizer, and the point has weight which is non-zero. So in this way, you have shown that the boundary has positive measures, so this minimizer does not have an open representative. It has a closed representative because with respect to this measure and using this fact, you can always add the boundary itself to the minimizer, and the perimeter doesn't change. And yeah, so for this reason, you can always add the boundary itself. So the minimizer will have a closed representative, and it is still an extension domain, but it doesn't have an open representative. And the second example, if I am still on time, am I?
Yeah, definitely.
Okay, good. And the other example is telling us that even if we have an open representative, it might be not, it might not be a BV extension set. So the example is somehow similar. Still, you have, in this example, your space is made of like 3 copies of these 3 planes, which are glued along this, say, unit interval here. And the distance we are putting on the space is just the Euclidean 1 norm on each of the planes. And the measure is twice the Lebesgue measure on this square x1 and just the Lebesgue measure on the other 2. And the domain we are looking at is made of the square. And then in the plane x2 and x3, we are attaching again triangles, where now the common part are those ones here. And here we are scaling appropriately, and here we are also scaling it even more. So, and in this case, you can show that actually the minimizer of the function, a minimizer of the functional is the domain itself. Why? Because we can show that functional computed at omega is less or equal than 2, while for any other subset, we can show that the functional has value which is greater or equal than 2. So let me show you just to see, because this has been shown just by using the very definition of the perimeter by the Lipschitz, by approximating by Lipschitz function. So to see that the functional computed on omega is less or equal to 2, first notice that the part of the measure which is in the functional we don't see, because it's omega minus omega and it's 0. So we are getting only the perimeter of omega. So to see that this is less or equal than 2, given that the perimeter is infimum among the limits of the sequences of such kind of things. So we just need to exhibit a competitor for which this is going to be less than 2. So now we can take as a competitor for the definition in the perimeter functions which are 1 on omega, and they are 0 outside of the neighborhood of the 1 over n neighborhood of omega. And this 1 over n neighborhood of omega now, with respect to the distance we are putting on our space, is going to be nothing but, if you imagine here, the same boundary, just 1 over n thick. So this is where we use the distance is precisely this. So now if you want to compute what is the energy of those approximates of the characteristic function of our domain, the energy of this is nothing but at n, which is a slope, which is the asymptotic Lipschitz constant of this function, times the measure of this neighborhood, which is as the neighborhood is such as I said, it can be computed and seen to be 2 over n. So if you multiply it, you are getting exactly 2. So you, given that the perimeters is the infimum among all the sequences which approximate the characteristic function of omega, then you are getting that it is less or equal than 2. And in order to show this inequality for any other set, you have to, again, to take any approximate of a characteristic function of any set you fix. And in that case, you are using this property of the measure, that you are doubling the Lebesgue measure here, and you will get this. But this is a little bit more technical to say. And in order to see now that this is not an extension domain, what we are going to do, we are going to show that this does not have extension property for the sets of finite perimeter. And it's enough to consider one of these triangles, anyone you want. So triangle is just one with the unit length, and then we are dyadically scaling this and putting it here. So now take any of your triangles, and notice that if you look at the perimeter in omega of the triangle itself, then this perimeter will going to scale as 2 to the minus 4k, because the scaling is like those slits here, while the perimeter in the whole space is going to scale like this side of triangle, which is 2 to the minus 2k. So if we compute this ratio, the ratio is going to be greater or equal to 2 to the power 2k, which blows up as k goes to infinity. So we cannot find a constant in order to satisfy the property of being the extension set for the sets of finite perimeter. So this is the thing. And as I said, PI spaces have some. In PI spaces, we have some better properties, and in PI spaces, actually, the functional like this has been already recently studied, or a variant of it has been studied in connection with the isoperimetric problem in the setting of metric measure spaces with curvature bounds and additional assumptions on the measure. And what can be shown is that if we are in a PI space and we have a minimizer of a function of f lambda, it is going to be a quasi-minimal set. I'm not going to define it now, and it has been studied by Kinnunen, Cortes, and Mungaling and Loren, and they have shown some topological properties for this kind of set, among which the topological boundary coincides with the essential boundary. So this means that these kind of sets have both open and closed representative. So if we are in PI spaces and we take a minimizer of our functional, then we know that and the proof of this implication can be found in the recent paper by Antonelli, Pasqualetto, Pozzetta, for instance, that they are quasi-minimal. And so we know that they have both open and closed representative. So it's closed. So the closed representative of such functional is going to be our BV extension set. So now there are many questions remain after study of this functional in this generality of metric measure spaces, and one of them could be: so is the closure of a minimizer of our functional, or is a closure of a quasi-minimal set a BV extension set? So, and with this question, I can finish.
All right, thank you very much, Danka, for this very beautiful talk. So, are there any questions among the audience before I shoot a couple?
I have a question. So, I mean, it's not about all the results that you presented, but or your new results, but it's about this a formula by Ambrosio, in which you see the perimeter as the n-1 Hausdorff measure.
Yes.
Restricted to the essential boundary. And then you have this theta. So why does this theta appear here? Well,
that's a good question, but I wouldn't really know to tell you why is this.
I see.
So
yeah, because
the point is it appeared, and also the fact that it depends on the set itself is also another issue, which is really subtle.
Yeah, because
but I really didn't get much into details with ever.
I see. I mean, for currents, there is this multiplicity that is an integer multiplicity, and then one has to multiply the Hausdorff measure by something that actually is telling you what happens with the tangent space So yeah, my question was if this was related to the tangent space.
Yeah, I put
that-
this as just as a side comment, just to say that if you work in this generality, then the situation is much more complicated. So you have really this density function that you don't know much about, but yeah.
Okay, thanks.
Thank you.
Any other questions? I think Juan Carlos has a question.
Yeah.
Yes, thank you very much, Danka, for your beautiful talk. I have one question. I am not an expert in these metric measure spaces, but do you think that your results, the Subole extension results, could translate it to the set of higher order Subole spaces or fractional Subole spaces? Because and what is the equivalent to this Lipschitz constant in order to handle higher order derivatives or fractional derivatives? It's understood, or what happened there?
Well, this I really never heard anything about, like going to higher order the derivatives apart from.
Yeah, that's
what maybe there might be some results by Koskela, but I am not sure.
Okay.
At the moment, I am not sure. But if you are interested, I can try to send some references.
Thank you very much. Yes, because that's a question that I had a long time ago, and now if you don't have let's say an equivalent for higher order differentials, but if you consider and you have the equivalent of first order differential, well, that this is the Lipschitz constant and all that, do you think that you can try to you can obtain a fractional differential when your exponent, your fractional exponent, is below 1?
Okay, I see. Well, so I guess that so this is a very good question, and it makes sense, but I would really don't know whether what to say. So it's
thank you.
But yeah, I will have a look. Maybe there might be something in the literature. I was concentrated mainly on this BV stuff and the Subole in the sense.
Thank you very much.
Thank you.
Are there any other questions? So I have one which is probably very naive, probably very silly. So in some settings you mentioned that actually the extension operator is linear, right? Is it possible to ask like a converse question, like say that I a priori assume that the extension operator is linear or has any other properties? Can I say something about the space or like the?
Yes, this one can also ask, but actually, so what do they prove when you say that the operator is linear? So what is equivalent is the existence of the extension operator. Then once you have one, then if in the Subole case p greater than 1, if you have an extension operator, then you also have a linear extension operator. So this is
I see. Okay, I see.
But if I assume a priori that I have linear extension operator, then I don't know what if anyone studied what does this say about the space.
I see. Okay, well, thank you very much, Danka. It was a very beautiful talk, very interesting problem. And so, okay, so thank you everyone for coming to the last session. And so we will resume the next semester.